Let us consider example 1, where we want to construct a system of equations to solve for mesh currents I1 and I2. We are given the following circuit. We have a voltage source that is connected to R1 at node A, and R1 is connected to R2 and R3, which exist in a parallel configuration at node B. To do this, we'll follow a simple 4-step procedure. The first step is to construct n KVL, or mesh loops. We see we're already given a mesh loop 1 and a mesh loop 2. It is noted for this class that we will always draw our mesh loops in the clockwise direction. We see that I1 follows our mesh loop 1 and I2 follows our mesh loop 2. Our second step is to assign voltage potentials consistent with our passive sign convention. And we should not duly label shared elements. That is, we are going to start sequentially with our loops and assigning our voltage potentials. That is, if we follow loop 1, starting in the bottom left-hand corner, we first encounter R1, and we'll assign our voltage potential consistent with the passive sign convention. As we leave R1 and proceed down, we encounter R3, where we'll assign our voltage potential consistent with our passive sign convention. Now when we assign the voltage potentials for elements associated with mesh 2, we start at the bottom left-hand corner and we see R3 is already assigned. That is, I2 enters a negative terminal associated with R3. Therefore, we will not reassign these values. We will leave it as is. Then as we encounter R2, we will assign our voltage potential and finish constructing our loop. Our third step is to write our n KVL equations, describing each mesh current. That is, for our first mesh current, we will construct a KVL equation based upon Vs, V1, and V3. That is, minus Vs plus V1 plus V3 is equal to 0. Now if we look at our second mesh current, we will construct a KVL equation, making sure we follow the correct polarities of our voltage drops. As we start in the bottom left-hand corner and move in a clockwise fashion, we first encounter minus Vs, and then we encounter plus V2, and this is equal to 0. Step 4 is to apply Ohm's law to express our voltage potentials in terms of our mesh currents and our resistances. That is, for mesh current 1, recall we had V1 plus V3 was equal to Vs, where V1, in terms of Ohm's law, is equal to our mesh current I1 times our resistance R1. Now V3 is resistance R3 times the net current running through it. That is, if we had a current I running through resistor R3, I would be equal to I1 less I2. That is, R3 shares mesh currents I1 and I2. Therefore, our KVL equation becomes I1R1 plus the quantity I1 minus I2 times R3 is equal to our source voltage. When we construct our mesh current 2 equation, i.e. our KVL equation, expressing our voltage potentials in terms of our mesh currents and resistances, we have minus V3, where we have V3 that's already expressed from our first KVL equation, plus V2, which is mesh current I2 times resistance R2, is equal to 0. Now we have a system of equations such that R1 plus R3 times I1 minus R3 times I2 is equal to our source voltage, our first KVL equation, and minus R3 times I1 plus R2 plus R3 times I2 is equal to 0, our second KVL equation.